Hey, this is chapter 21, Fundamentals of Machining, and starting from this chapter, we will be talking about the fundamentals, the basics of machining, and then later we will discuss some other machining processes like turning, milling, drilling, and for about 6 weeks, we will be discussing such topics. And as you see in this chapter, we will be covering most of the sections, and I would like to start quickly. Let's start with some example machining operations. And what we do in this machining operations, we need to use a tool. As you see here in all of these, we have cutting tools. This is an example of a little insert, a kind of a cutting tool. And with the help of these cutting tools, they have sharp edges, and we try to remove material, we generate some chips, little chips sometimes continuous, discontinuous chips, we will talk about them. And once you generate, remove material from the initial workpiece, you will be doing a machining operation. And here you see some common examples. The first one is called as straight turning. We have a tool here, and this tool is moving, as the name implies, straightly in a straight manner from right to left. And depending on the required dimensions, your tool may go into this workpiece a little bit, and at the same time, this part is rotating. And this is another important issue in machining. We need to have a relative motion. The tool and the workpiece both cannot be stationary. If that's the case, then we cannot talk about machining. One of them should be moving, rotating, and the other one might be stationary, or it may be just moving. And in this turning case, as you see, we'll discuss the details in the next chapters, but right now we can say that since it's a turning operation, the workpiece should be turning at very high speeds, and the tool is being fed this time from right to left. And if you look at the cutting off operation, this operation can be handled on the same machine, same turning machine, but this time the tool is not moving to left or right, it's directly moving into the workpiece. And again, with the help of these cutting edges, we can generate chips and decrease the thickness of this neck, diameter of this neck is reduced, and at some point, this right portion will be cut off. If you look at the below ones, we have milling examples. The first one is slab milling. And in the slab milling, the axis of this cutting tool is actually parallel to the surface being machined. This is the main difference with respect to the end milling. And as you see, depending on the width of your cutter, you may remove this part of material maybe in a single motion. And if you look at the end milling this time, the axis of rotation of our cutter is perpendicular to the surface to be machined, and we have again this tool moving inside the part and removing material. And if you compare the below ones with respect to the upper ones, this time our workpieces are not rotating. They may be just moving in X, Y directions, but they're not rotating. The cutting tools are rotating. And these machining operations, we have some important terms, like here, as you see, this is a turning operation. We have depth of cut. This is depth of cut, the amount of actually material we are removing from the outer surface, how deep actually we are embedding our tool into the workpiece. Then we have the feet as kind of at the speed of our tool. This tool is, as you see, in turning operation, moving from right to left, and the speed of that tool is named as feet. And sometimes you may simply name it as feet, which will be giving us the amount of tool moving, in this example, to left in a single revolution. But if you give this value in, let's say, millimeter per revolution, then it will be in feet rate. And this is how the chips are generated, as you see. And in the idealized actually models, we will be assuming that, and this one I will spend some time on this figure. This is actually the rotated view of figure 21.2. They are similar. Just the thing is that the terms, the names are actually a bit different here. Let me talk about this issue here. the feed in this turning operation here is actually equivalent to the depth of cut in this figure. So the parameters are actually reversed, and the depth of cut here is actually the width of our chips. So this width is actually the depth of cut and this turning operation. But the fundamentals are the same. We have the tool, we have a relative motion, and the chips are moving over the rake face. This is the rake face of the tools. Let's focus on this figure. This is a figure showing two orthogonal cutting processes. In the first one, we have a well-defined shear plane. In the second one, we don't have a well-defined shear plane. By the way, the orthogonal cutting means that the cutting edge is vertical to the direction of motion. So these are movements. Let me draw it. This is the direction actually we are moving, and the cutting edge is here, and this is perpendicular to the direction of motion. So that's why it's called as orthogonal cutting. But in real life, we prefer to have an oblique cutting, but the things are highly difficult, highly complicated in oblique cutting. So that's why we will keep it simple and always focus on orthogonal cutting. And here you see the workpiece, obviously in blue. We have chip generated here. It's again blue since it's made of same material. We have the tool. This is in gray. And we have many parameters, as you see. Let's start discussing one by one. This is the workpiece, as I mentioned. This is our depth of cut, T0, or we can say that this is the initial chip thickness or the undeformed chip thickness, T0. Then we have shear plane here. The deformation actually starts on this plane. After this plane, material starts moving, and the angle between the horizontal surface and the shear plane is called as shear angle. And we use the letter phi here. And chip is, as you see, moving on the rake face of the tool. The tool has some faces. This part is called as rake face, and it has another face underneath. This is called as flank face. And the chip, while it's moving, its thickness is increased. This is called TC, the chip thickness, the actual chip thickness after it is generated, and it is larger than T0. Okay, this is an important issue. The generated chip has a thickness larger than the undeformed chip thickness T0. And due to the deformation, obviously, we have rough surfaces on this side, but we have shiny surface on the back side. Since we have friction, due to this friction, we have smoother surface at the back side of this chip. And let me discuss some angles, the most important angles of the tool. Here you see we have an angle called rake angle. Since it's the angle between the vertical plane and the rake face, that's why people call it as rake angle. We use the letter alpha to define this angle, and it is positive in the clockwise direction, and it is negative in the counterclockwise direction. Okay, it is 0 when the rake face is vertical. And we have another angle. The other angle is between the flank face and the machined surface. This is called as relief angle sometimes, or sometimes clearance angle, and its value is usually around 3 to 5 degrees, but it cannot be less than that. If you decrease the clearance angle, then we are going to actually have friction between the machined surface and the flank face of the tool, and this is not desired. Since what happens if you have friction, then that means you're going to generate heat, and this heat will deform the surface of the machined regions. And I think I mentioned all the things here. Yes, that's how we look at this one. We don't have a perfect shear plane. Instead, we have a shear zone, and this is called as primary shear zone, since we may have other shear zones around, but this one is the most important one since the deformation starts in this primary shear zone. let's briefly discuss the parameters, affect the variables actually affecting the cutting process. And we have independent parameters and dependent parameters. Independent means that they're not affected by other parameters, but the dependent parameters, dependent variables are always depending on these independent variables. What are these independent variables? For instance, in this cutting process, you can change the tool material, you can apply some coating. So this is totally independent from other parameters like angle, quality. What about tool shape? Again, it's another independent parameter. The shape of it, the surface quality, the sharpness of the edges are all independent parameters. Another independent parameter is workpiece material. Since we decide on the workpiece material, its processing history is again determined by us. So it's again independent in the cutting process. Another independent variable set is cutting speed. It's a set by us again. The feed rate, the depth of cut, they are all independent variables. And other things like cutting fluids, since we are the one again deciding on the type of cutting fluids can be used in the process. So that's why they are again independent variables. And lastly, the characteristics of the machine tool, the type of the work holding device and fixturing are all examples for independent variables. But on the other hand, we have some dependent variables. What are these? For instance, type of chip produced. Whether we are producing a continuous chip or a discontinuous chip, segmented chip, they all depend on the independent variables. But again, it's a variable, but it's a dependent variable resulting from the values of the independent variables. Another dependent variable is the force and energy displayed during the cutting. And these are all determined with the help of independent variables. By setting the speeds, depth of cut, you can change the force and energy displayed during the cutting process. Other dependent ones are the temperature rise in the workpiece. It highly depends on, for instance, the speed, depth of cut, the type of material you are machining, the type of cutting tool material you are using. They will all affect the temperature rise in the workpieces. And obviously, you may further have temperature rise on the tool, on the chip. So they all depend on the independent variables. And then we have another set of dependent variables is the tool wear and the failure. Whether we're going to have some craters, some cracks on the tool, they all depend on these independent variables. The speed, the depth of cut will highly affect the cracks, craters on the cutting tool. We will discuss them in a moment. And the last dependent set of variables are the surface finish and surface integrity of the workpiece. Since, again, depending on the speed, tool, workpiece variables, they will affect the surface quality of the resulting part, resulting machine surfaces. And we have actually a nice orthogonal model for this process, a cutting model. There are many people actually doing research on the modeling of this cutting process, and we will be now in a moment discussing these details. And the most popular one is the merchant model. It was developed around 1940s, and it depends on the orthogonal cutting. Now let's have a look at it. This is another sketch actually summarizing the process, the cutting process. We have the shear plane, we have chip thicknesses, workpiece, tool, rake angle, clearance angle, but right now we are not going to use it in our analysis. What we are going to do actually, we will obtain a cutting ratio. And this cutting ratio is simply the ratio of the undeformed chip thickness and the actual resulting chip thickness TC. This is the chip thickness ratio, or I'm sorry, the cutting, chip thickness ratio. We can sometimes call it as cutting ratio. And as you see, it depends on the shear angle and the rake angle. And this is the angle we set during the operation, but shear angle depends on some other things I will discuss in a moment. If you want to determine, set your, let's say, shear angle to some specific values, then you may use this equation. But if you want to use this equation, then you need to know the cutting ratio. How we can determine cutting ratio, since you already set T0. T0 is a known value, it's depth of cut. And how we can determine TC? You can measure it after a machining is performed. You can take some chips, do the measurement, and if you simply divide these values together, you can obtain cutting ratio. Once you have it, then you can use this equation to determine the shear angle, if this is important for you. And this is describing actually what I mentioned a moment ago, but now I will talk about this equation, how we derived this equation. We have a much simpler sketch here. This one is quite complicated, not clear, so that's why I added another image here. This is again our workpiece. A chip is moving over the rake face again, the rake angle alpha, and this is our undeformed chip thickness, deformed chip thickness. This is TC, and we have shear angle here, and we made it kind of a little trick here. This is, by the way, this angle is, let me feel it, and this is alpha, right? And due to the similarity of triangles, this part, this angle, let me paint it. Yes, this is again alpha, okay? And that's why this part is, this region is phi minus alpha, okay? And this is our shear plane, AB. Now we are going to define this AB in terms of T0 and TC. So what is T0 equal to? It's equal to AB times sine of our shear angle. And we can also define the same AB by using the TC here. What is that actually? Or we can define TC in terms of AB. TC will be equal to AB times the cosine of this angle, phi minus alpha. Since this is 90 degrees, we have a right angle here. And that's why it's actually equal to TC. So if you simply write these two equations, then you can take the ratio of them and come up with the equation we have in our textbook. And this is, as I mentioned, you can easily determine the cutting ratio if you know the depth of cut. It should be known actually for the process. And if you do measurements on the resulting chips, you can simply determine the cutting ratio. Once you determine it, then you can use this equation above and determine the shear angle. Why shear angle is important? Since there are various actually, again, models, and in one model, they have kind of a relationship between the shear angle, rake angle, and the friction angle. The friction angle I will talk about in a moment, but it depends on the friction between the rake face and the chips moving over it. It's the friction, it depends on the friction coefficient on that surface, and it's equal to actually this friction coefficient of friction nu is equal to tangent of this friction angle. And what this equation says is that if you, for instance, decrease the rake angle, which means that you make it vertical, if that's the case, then we will be generating thicker chips. So what is the problem? If you generate thicker chip, then that means you're going to generate more energy, more heat will be generated, and things will be much difficult. So it's better you have less thicker chips generated during the manufacturing process. And what about the other case? If you increase, if you increase the friction on the rake face, then again, we will have thicker chips. And again, if you have thicker chips, then that means you will be dissipating more energy. And in the manufacturing process, actually, our main aim is to minimize the energy dissipation and minimize the cutting forces. Otherwise, once you have huge forces, then you may deform your machine, you may deform the cutting tool, workpiece, you will do lots of harm on the equipment and the work materials you are using. So that's why we always try to optimize this shear plane angle, and this is done actually with the help of this equation. And obviously the shear plane is the plane of maximum shear stress, so that we can start this chip removal process. These are all for the merchant model, and we will be discussing in a moment the types of chips produced in this machining process.